Okay, it's time to start. Clock is still not working. Today we're going to finish chapter 19. We'll spend most of our time discussing the acidity of carboxylic acids, their most important property. We'll also talk about extraction, a method of using solubility properties to separate carboxylic acids from other organic compounds. And then we'll conclude with a brief discussion of other types of organic acids, organic compounds that are not carboxylic acids that are also acidic. So most carboxylic acids have a pKa somewhere in between 4 and 5. I've drawn benzoic acid on the board here. Its pKa is 4.2. Acetic acid is slightly weaker. Its pKa is 4.8. But I've drawn for you an acid-base equilibrium with benzoic acid. In this case, we're using sodium bicarbonate as our base to deprotonate our carboxylic acid. And we learned from chapter 2 that acid-base equilibria are going to be favorable in the direction of forming the weaker acid and the weaker base. So if the pKa of our conjugate acid is higher than the pKa of our acid, then that reaction is going to be favorable. So this particular acid-base reaction, we could adjust the way we draw these arrows here to show that this is going to be favored. At equilibrium, we're going to have probably greater than 99% of the carbonic acid and less than 1% of our benzoic acid. Okay? So if we look at this table here, this table contains common bases whose conjugate acids are weaker acids than carboxylic acids, and therefore these bases would be able to completely deprotonate carboxylic acids. Sodium bicarbonate is cheap, it's baking soda, and so that's probably the most common one that's used because it's cheap and widely available, but you could use any of these bases. Ammonia, as well as some other amines with alkyl groups attached to a nitrogen, are also fairly widely used as ways of deprotonating carboxylic acids. Okay? So, based on our understanding of acid-base equilibrium, we understand why these bases would all completely deprotonate this carboxylic acid. So what we need to do now is review why carboxylic acids, while they are weak acids, they're significantly more acidic than alcohols. We have an OH group here that is acidic. In alcohols, we have OH groups that are acidic. But carboxylic acids are more than 10 orders of magnitude more acidic than alcohols. Why? You can tell us. Okay? Okay, the conjugate base of carboxylic acids is stabilized by resonance. We learned in chapter 2 that any structural feature that stabilizes a conjugate base makes the acid more acidic. This can be understood by recognizing that the conjugate base is a product of the acid-base equilibrium. And anything we can do to lower the energy of one of the products is going to make that more favorable in terms of thermodynamics. Okay? So resonance can stabilize or lower the energy of the conjugate base of a carboxylic acid. So let's draw acetate. This is conjugate base of acetic acid. And we have this other resonance structure that we can draw for acetate. These are equivalent resonance structures, meaning that they are equal in energy. And so that also means that the negative charge is shared equally between the two oxygens. So we can draw a hybrid structure. Looking like this. So we would have -1/2 charges on each of the oxygens. And then the two carbon-oxygen bonds are going to be equivalent to each other. They're going to have a 1.5 bond order. And so their bond lengths are going to be the same. And that is 1.27 angstroms. Okay. So when we have equal contributors, we have the maximum amount of stability according to resonance. And so that makes the conjugate base of acetate much more stable than the conjugate base, or acetate, the conjugate base of acetic acid, much more stable than the conjugate base of ethanol. So ethanol's pKa is 16. Acetic acid's pKa 4.8. So a dramatic effect due to the resonance stabilization of the conjugate base. We have another molecule, phenol, with intermediate acidity. The pKa of phenol is 10. Okay? Why is phenol significantly more acidic than ethanol? Who can raise their hand and tell us? Okay, great.
Resonance can delocalize the lone pair of electrons throughout the ring.
So we want to look at the structure of the conjugate base. Let's draw the conjugate base of phenol. It's known as phenoxide. Okay. Can we delocalize the negative charge in phenoxide due to resonance? Yeah, anytime we have a lone pair adjacent to a benzene ring, we can delocalize that lone pair into the benzene ring. Okay. So we end up with the negative charge now on a carbon in the ring. And then we can move that negative charge around the ring. And we can move it to one more carbon. So how many atoms are sharing the negative charge in phenoxide? Okay, 4 atoms, this oxygen and these 3 carbons. So we can draw a hybrid structure. We have dashed lines going all around the ring. Dashed lines here. Partial charges. These 4 atoms. Okay. Are these resonance structures equal in energy, or is there a major contributor? Yes?
Is the first the major contributor?
First is the major contributor. Why?
Because of aromaticity.
Yeah, there's 2 reasons. One is this resonance structure is aromatic. These 3 are not. The other one deals with which atom bears the negative charge. We learned in chapter 2 that negative charge is more stable on a more electronegative atom. So it's better to have the negative charge on oxygen than to have it on the carbon. So for 2 reasons, we have a major contributor and 3 minor contributors. So if we look at our hybrid, what this means is that the magnitude of the partial negative charge on the oxygen is going to be closer to 1, and the magnitude of the partial charges on the carbons is going to be closer to 0. Okay? So we have resonance stabilization, delocalization of the negative charge. That explains why phenol is more acidic than ethanol. No resonance stabilization of the conjugate base of ethanol. But we have a major contributor and 3 minor contributors instead of equal contributors. That explains why phenol is less acidic than acetic acid. Okay, here we have equal contributors in the conjugate base. We have a higher degree of stabilization due to resonance. So we have a nice figure from the book that shows us the resonance structures of phenoxide. You'll notice that the book drew 2 resonance structures with the negative charge on oxygen. I only drew 1. While these are both resonance structures, when we're considering the stability of the conjugate base, we only need to look at resonance structures that are moving the negative charge. Right? When we go from 1 to 5, the negative charge is in the same place, so that's not contributing to delocalizing that negative charge. So that's why I only drew 4 on the board and there's 5 here. We have the negative charge delocalized on 4 atoms. One good point about this figure is it shows us that the hybrid is always lower in energy than the individual resonance structures. So here we have major contributors here, minor contributors up here, and the hybrid is lower in energy than even the major contributors. We always have stability caused by delocalizing the electrons. So this is going to be more stable than if we had just one individual resonance structure of phenol. Okay? We have another figure here that summarizes these 3 compounds. And it points out that it doesn't matter if you say 3 or 4 here. We know that we can draw more resonance structures of phenoxide than we can of acetate. So it's not the number of resonance structures you can draw, it's whether you have major contributors or whether you have equal contributors that determines the degree of stabilization you will get from resonance. We have a higher degree of stability due to resonance with acetate because we have equal contributors. With phenoxide, we have a major contributor and 3 minor contributors, so the degree of stabilization due to resonance is not as high as it is with acetate. So phenoxide, less stable than acetate, therefore the acid is less acidic, and then ethoxide is the least stable of all, no resonance structures, and therefore ethanol is the least acidic. Question?
With 2 molecules that have resonance structures with equal contributors, would the one that has the most negative atom be the most resonance stabilized?
Yeah, you'd have to look at other factors. We'll do an example later on in the class where we can compare 2 acids where their conjugate bases have equal contributors. So we'll go through an example later on in class that might answer your question about that. So we can go back to our chart, our table. We've got the pKa values for ethanol, phenol, and acetic acid on the board. We know that all of these bases will completely deprotonate acetic acid. What about phenol? What is the weakest base in this table that would completely deprotonate phenol? You can raise their hand and tell us. The weakest base in this table that would completely deprotonate phenol. Okay, great.
Na2CO3.
Okay, Na2CO3. Yes, you're correct, although I wouldn't use this one because that's so close to phenol, you'd probably get a 1-to-1 mixture of the acid and the conjugate base. So while technically your answer is correct, I would actually go with methoxide. A 5 order of magnitude difference in acidity means you're going to get well over 99% deprotonation of phenol, whereas with sodium methoxide, you get somewhere between 50 to 60% deprotonation. Okay? So methoxide, hydroxide, ethoxide, hydride, any of those bases would fully deprotonate phenol. Which base would fully deprotonate ethanol? Yes? Yeah, hydride, H-, that's the only one, right? Ethoxide, of course, you'd get a 1-to-1 mixture. That's the conjugate base of ethanol itself, so you'd have to go with sodium hydride if you wanted to fully deprotonate ethanol. All right, so the book tells us about the Henderson-Hasselbalch equation, which is something that you've presumably learned previously in general chemistry. We're not going to use the Henderson-Hasselbalch equation quantitatively. We're not going to calculate anything with that equation. We're going to use it qualitatively. Its most useful aspect in organic chemistry is allowing us to predict which species will dominate in solution at a given pH. You have an equilibrium between an acid and its conjugate base. And at different pHs, you're going to have differing concentrations of the acid and the conjugate base. So what the Henderson-Hasselbalch equation tells us is that if the pH of our solution is less than the pKa of our acid, then the acid is going to be the dominant species in solution. Okay. So if we look at benzoic acid, we have a solution of benzoic acid in some aqueous buffer at various pH. If the pH of that solution is below 4.2, we have a high concentration of acid, a low concentration of base, and therefore that means we're going to have a higher concentration of benzoic acid than we will of benzoate, its conjugate base. And then the converse is true. If we add base to our solution and we raise the pH above the pKa, now that higher concentration of base is going to deprotonate our carboxylic acid, and then the conjugate base form is going to dominate. Okay. So that's what we're going to use the Henderson-Hasselbalch equation for, just qualitatively to predict whether an acid or its conjugate base is going to be the major component in solution at a given pH. Any questions? All right, we've talked about how resonance impacts relative acidities of compounds. Let's talk about inductive effects. Again, this is a review of something we learned back in chapter 2. So inductive effects are effects caused by atoms that are not bonded to the acidic atom. They're a little more remote in the molecule. And our conjugate base is negatively charged, so if we have electron withdrawing groups that are going to, those are going to be able to stabilize that negative charge in the conjugate base. But if we have electron donating groups, then that would destabilize the negative charge in our conjugate base. Okay? So if we're looking at chloroacetic acid, would chloroacetic acid be more acidic or less acidic than acetic acid itself? More acidic. Why? Okay, we have to look at the structure of the conjugate base. This is our conjugate base. Okay. Of course, we could draw a resonance structure, but we could draw that same resonance structure with acetic acid. So we don't have any extra resonance structures with chloroacetic acid. But what we do have is a polar bond polarized towards the chlorine. So that means that this carbon, which is adjacent to our carbonyl carbon, has a partial positive charge. That partial positive charge can stabilize the negative charge of our conjugate base. Okay, so that's an inductive effect, stabilizing the conjugate base of chloroacetic acid. The pKa is 2.8. So most inductive effects are 1 to 2 pKa units. Some of them are less than 1 pKa unit, much less dramatic than resonance effects. But chloroacetic acid is about 100 times more acidic than acetic acid because of inductive stabilization of the negative charge due to this electronegative atom, this polar bond. Okay? Let's add a couple methyl groups to acetic acid. This is called pivalic acid. Is this going to be more acidic or less acidic than acetic acid? Less. Why? Yes, Trent.
Because the methyl groups like donate electrons over there, and so it's
Yep.
going to be more unstable.
So we've learned in a couple of settings that alkyl groups are weak electron donating groups. Right, we learned that back when we learned about carbocations in 351, and we reinforced that in our last chapter with alkyl groups being weak donators and weak activating groups in electrophilic aromatic substitution. So when you compare pivalic acid to acetic acid, these two extra methyl groups are going to donate electrons. Therefore, they're going to destabilize that conjugate base. So the pKa, in this case, is 5.1. So not a big difference, 0.3 pKa units, but a measurable difference in acidity attributed to the donating effects of those methyl groups. Okay? So a couple of factors to remember about inductive effects. They are additive or cumulative. So if we have additional electronegative atoms, 2 or 3 electronegative atoms, then that's going to stabilize our conjugate base more and lead to a stronger acid. So dichloro, trichloroacetic acid would be stronger acids than chloroacetic acid. They're dependent upon the electronegativity of the atom. So if we had a more electronegative atom than chlorine, we'd have a stronger inductive effect in a more acidic species. They're also dependent upon the distance of that atom from the negatively charged species. So if we had a longer carbon chain connecting our chlorine to our conjugate base, our carboxylate, we'd have a weaker inductive effect. Okay? Any questions? All right, so we should be able now to get out our eye clickers and compare these 4 carboxylic acids and choose the one that is the most acidic. You may go ahead and talk to your neighbors to answer this question. Okay, let's try to get our final answers in the next 15 seconds or so. Answers? Good. Right. Any more? Looks like everybody for today, so we'll go ahead and stop this. All right, which one's the most acidic? C. Why? Who can tell us? Don't be shy. Yes?
Chlorine is the most electronegative.
Okay, so we have all these halogens. We have a single halogen at the same position in the chain in each case. So we're just going to compare the electronegativities. And the fluorine is more electronegative, therefore it has the strongest inductive effect, the highest degree of stabilization We wrote the pKa of chloroacetic acid up here. It's 2.8. The fluoroacetic acid would be 2.6. I have it in my notes. So measurably more acidic than A. So we can also have inductive effects on the relative acidities of benzoic acid derivatives. Okay? So based on what we learned in chapter 18 about substituents on benzene rings and whether they donate electrons to the benzene ring or withdraw electrons from the benzene ring, you should be able to answer this question. Cursor here. Start this up. Again, go ahead and talk to your neighbors and select the most acidic carboxylic acid here, combining what you learned in chapter 18 with what we are discussing in this chapter.
Because D is an electron donor. Because there's three. Oh wait, no. Yeah, no. There'll be a single bond in that carbon. That carbon has three bonds. D is C or D. Because A and D are both going to be metal. I mean, but C is going to be due to oh wait, no. C is an electron donor. Yeah, it's a donor. That would make at least that last. Okay, yeah. So then we would want withdraw electron. So yeah, no, it's not C. It's the opposite. So it'd be A. Yeah. Because C is an electron donor. Well, yeah, NO2 would be electron donor. No, wait, NO2.
That's what I'm
Isn't that electron withdrawing? I thought NH2 is a donor. NO2 is withdrawing. That's it. It's a deactivated to electrophilic addition to the receptor substitution.
Okay, let's try to get our final answers in the next 15 seconds or so.
Is D withdrawing or is it donor?
I think the average last 2 years ago was low center high 70s.
Yeah, NO2 is withdrawing.
Okay.
know like all of the past stuff.
There's one more answer out there. 27 was the last question.
But like, like MC
Going once.
like the norms, I feel like you can do.
There we go. All right, we'll close it off. This question prompted a little more debate than the last one. As I was watching the answers, there was some debate between a few of the choices before we coalesced mainly around a single answer. So there was some discussion between A and C, but ultimately most people decided that C is the most acidic of these compounds. Who would like to raise their hand and explain why they decided that C is more acidic than A? Yes, please.
Remembering that chart about the strength of the withdrawing groups and donating groups.
Okay.
The NO2 is further down, whereas the chlorine is weaker.
Okay. So we had a table in chapter 18 that showed us a hierarchy of activating and deactivating groups. We know that the more deactivating a group is, the stronger it is at withdrawing electrons. And so therefore we should have a stronger inductive effect on acidity. And so you knew that NO2 was lower down on the chart than chlorine or any of our halogens. And so this would be the stronger electron withdrawing group and therefore the strongest acid because you'd have the highest degree of stabilization of the conjugate base. Remember that this nitro group has an atom with a positive charge attached to the benzene ring. It also has a nitrogen-oxygen double bond that can be used to withdraw electrons from the benzene ring. Whereas our halogens donate by resonance and withdraw by induction. So they're not as strong at donating they are not as strong at withdrawing electrons from the ring as the nitro group is. And then, of course, our ethers are donating groups. Those donate by resonance. They can withdraw by induction, but they're stronger donating groups. Okay, so the stronger of an electron withdrawing group, or in other words, the stronger of a deactivator that group is, the more acidic the benzoic acid derivative will be. Any questions? So there was a sample problem in the book that's very similar to this. It was asking you to put benzoic acid, paramethoxybenzoic acid, and paranitrobenzoic acid in order in terms of relative acidities. We had these two on our iClicker question. And so we would know that paramethoxybenzoic acid is the weakest acid, paranitrobenzoic acid is the strongest acid. To explain that, the book is drawing some resonance structures here for you. These resonance structures are showing you that you can delocalize this lone pair into the benzene ring, and that gives us a negative charge in close proximity to the negative charge on the carboxylate. That's going to be bad, having those two negative charges close together, destabilizing the conjugate base, meaning that paramethoxybenzoic acid is less acidic. On the contrary, with paranitrobenzoic acid, we have this pi bond. We can use it to withdraw electrons from the benzene ring, giving us a positive charge, a resonance structure with a positive charge close to the negatively charged oxygen. This is stabilizing, meaning this conjugate base is more stable, and paranitrobenzoic acid is more acidic. It's important to note that even though we're drawing resonance structures here, this is an inductive effect. This is not a resonance effect, because these resonance structures are not delocalizing the negative charge. They're simply moving a charged atom closer to the negative charge, which is either raising its energy or lowering its energy. So it's kind of tricky, but we're using resonance structures to illustrate an inductive effect in this case. And we know it's an inductive effect because the differences in acidity are not very big. We've got benzoic acid's pKa on the board, it's 4.2. Paramethoxybenzoic acid is 4.5, so it's only 0.3 pKa units higher, very modest effect. Paranitro is 3.4, so it's less than 1 pKa unit more acidic. So these are modest effects, they're inductive effects, even though we're using resonance structures to show them. These resonance structures are not delocalizing the negative charge, they're just either stabilizing or destabilizing it by moving charged atoms close to the negatively charged oxygen. Any questions about that? Okay, so you should be proficient now in comparing relative acidities of acetic acid derivatives or benzoic acid derivatives. Let's talk now about a technique that those of you who are taking the 354 lab have learned about, and that is extraction. Okay? Extraction is a technique that we use to separate organic compounds. So it's the use of solubility properties to separate compounds. Sometimes we can separate inorganic compounds from organic compounds. Sometimes we can separate two different organic compounds from each other if they have different solubility properties. We can actually use acid-base chemistry to change the solubility properties of organic compounds. First of all, I'll show you this figure here. When you perform extractions in the 354 lab, you're using a small little vial, right? And you stir, you mix your two layers. You have an organic layer and an aqueous layer. You mix them up by stirring, and then you use a little pipette to pull off the top layer. Well, in a research lab, we have a better piece of equipment known as a separatory funnel. and the separatory funnel has a stopcock on the bottom that allows you to drain the solution out the bottom. And that's a lot easier than pipetting it off the top. So we have our 2 layers here. If we open the stopcock, the more dense solvent will come out. Now, I asked a couple questions in the last class period, and I found that in the 354 lab, you have been using dichloromethane as the solvent for doing your extractions. It's important to note that dichloromethane is the only one of the common organic solvents used for extractions that is more dense than water. In my lab, ethyl acetate is probably the most common solvent used for extractions, and it is less dense than water. Ether is another one that we use sometimes. Ether is also less dense than water. Most organic molecules are less dense than water. Chlorinated, because chlorine is a heavy, dense atom. If you have chlorinated molecules, that will make it more dense than water. So when you're doing an extraction, it's very important to remember which solvent you're using and know whether or not that solvent is more dense or less dense than water, because the aqueous layer is often on the bottom in your separatory funnel. So the way you can use your separatory funnel, as well as acid-base properties, to separate organic compounds is shown on this figure. Okay? So here we're separating benzoic acid from cyclohexanol. They're both polar organic molecules. They'll dissolve in a polar solvent, dichloromethane. Are these molecules going to be water soluble? No. How many carbons in each case? 6. 6 carbons, 1 functional group capable of hydrogen bonding, so insoluble in water. But if we add aqueous base, sodium hydroxide, we know that sodium hydroxide is a strong enough base to fully deprotonate that carboxylic acid. Will it deprotonate the alcohol? No. It will not. So we add 10% sodium hydroxide, we now have a carboxylate salt of our acid. We have its conjugate base, and we have the alcohol. When we have a salt, an ionic functional group, now that 5-carbon rule goes out the window. Salts are going to be soluble in water. They're not infinitely soluble. There are limits. Right? If you had a 30-carbon chain, it probably wouldn't be soluble in water. I don't know the exact number. But molecules that we're studying in this class are going to be small enough that we can conclude any carboxylate that we see in this class is going to be water soluble. Okay? So we've made this ionic functional group, we've made this into a salt, and now it is water soluble. So that goes into the aqueous layer, the alcohol stays in the organic layer, we separate them, we drain the organic layer out the bottom, and then we're going to close the stopcock and pour the aqueous layer out the top into a different Erlenmeyer, and now we have our 2 compounds separated. If we wanted the carboxylic acid instead of the carboxylate, we would just add some acid to this solution to turn it back into the carboxylic acid. Okay. Any questions on how you would use acid-base properties to separate a carboxylic acid from another organic compound? Okay. This is very useful. It's frequently done in research labs. Okay. So carboxylic acids are probably our most common organic acids, but they're not the only ones. So the rest of the time we'll spend discussing a couple of other classes of organic acids that we will learn about, that we'll encounter in the class. One that we've seen already is the sulfonic acid. Okay? We learned how to make benzene sulfonic acids in chapter 18. We can do a sulfonation. And there's a very common benzene sulfonic acid that we learned about in 351M, and that is para-toluene sulfonic acid. Now we understand the name. Right? This is toluene right here, and we've attached a sulfonic acid. And the groups are paired to each other, so that's why this molecule is called para-toluene sulfonic acid. So we understand the name now. We're still going to use an abbreviation because we don't want to write para-toluene sulfonic acid. And so PTSOH refers to this compound. So if we treat it with a base, we deprotonate the OH. In the interest of time and space, I'm going to abbreviate the toluene group as R. Okay? So here's our conjugate base of toluene sulfonic acid. Toluene sulfonic acid is a strong acid. pKa is -7. So you're talking about between 11 to 12 orders of magnitude more acidic than a carboxylic acid. Why? You can raise their hand and tell us why. Yes?
There's one more oxygen.
Okay. So we can have resonance stabilization of the conjugate base of a sulfonic acid. We have 2 oxygens we can delocalize that negative charge onto instead of just one with the carboxylic acid. So we'll draw the resonance structures. That was the negative charge from last class period. It didn't get erased. We drew it in the same spot. Okay. And then we can delocalize it onto this oxygen as well. Okay. And then, of course, we get the conjugate acid of whatever base we used. So here we have 3 resonance structures. We told you earlier it's not necessarily the number of resonance structures that matters. It's whether or not you have equal contributors versus a major and a minor contributor. But if in both cases you have equal contributors, the more equal contributors you have, the more resonance stabilization. So here, because this negative charge is shared equally by 3 oxygens, they would each have a -1/3 charge in the hybrid. Whereas with acetate, we have a -1/2 charge in the hybrid on each of the oxygens. Okay? So we have greater resonance stabilization of the conjugate base of sulfonic acids compared to carboxylic acids. And that's why they are very strong acids. Any questions? Yes?
Isn't the methyl group an electron, like likely electron donating? So if the methyl group wasn't there, would it be a stronger acid?
Yeah, so if you had benzene sulfonic acid, it would be a stronger acid, probably by 0.1. It would probably be like 7.1 or something like that. So it wouldn't be a huge effect. But yeah, if you were to compare those, indeed, benzene sulfonic acid would be slightly more acidic due to the weak donating effects of the methyl. All right, another class of organic acids are derivatives of an inorganic acid, which is phosphoric acid. So we'll draw phosphoric acid on the board, H3PO4. It has 3 acidic oxygens, and so we have 3 pKa values. To pull off one of those, we have a pKa of 2.1, so that's weakly acidic, but more acidic than a carboxylic acid. And then to pull off the second one, to make a dianion, the pKa would be 6.9. And then to fully deprotonate phosphoric acid, to make phosphate, we'd have to get up above 12.4. Okay? So, in biochemistry, we have lots of molecules that are phosphoric acid esters. They have some sort of an R group replacing one of the OHs. We have phosphodiesters as well. DNA and RNA have those in their backbone. But if we're looking at phosphoric acid esters, these are a couple of common ones: glucose 6-phosphate, glyceraldehyde 3-phosphate. We'll encounter these molecules later on in the class. when we study metabolic pathways. But what we see when we look at their structures is they're typically drawn with 2 negative charges as the dianions. And that is going back to the Henderson-Hasselbalch equation. Physiological pH is typically about 7.4. Most of the aqueous solutions in our body are weakly basic. And if we look at these pKa's, we've got 2 of them drawn here on the screen. I drew 3 on the board. This pKa is above pKa2 of phosphoric acid. So that means that the dianion is going to be the major species in solution at pH 7.4. So according to the Henderson-Hasselbalch equation, we know that the dianion would be the major species of phosphoric acid esters, and that's why they're drawn typically as the dianions, because that's the major component that we would have in solution. Okay? Our final class of organic acids is actually a subclass of carboxylic acids, and that is the amino acid. We'll learn much more about amino acids later on this semester when we study amino acids, peptides, and proteins. They're the building blocks of peptides and proteins. In these last couple of minutes, we're just going to focus on their acid-base properties. Okay? So as the name suggests, an amino acid has both an amine and a carboxylic acid. And then this is known as the alpha carbon, and we have R groups coming off the alpha carbon. We have 20 common amino acids that have the same structure that just differ in the nature of the R group. But amino acids don't look like this in solution. This functional group is acidic, this functional group is basic. So what happens is you would have a proton transfer between those functional groups. And the most stable form would be this species with 2 formal charges, which is known as a Zwitterion. This is a German word. Zwitterion means internal salt. So if you have a molecule with 2 charged atoms, that's an internal salt, or a Zwitterion. Okay? If you look at the pKa of the ammonium group, that's usually 9 point something. pKa of a carboxylic acid, usually 4 point something. In the case of an amino acid, it's lower for reasons we'll learn later on in the class. But this is a weaker acid than that, so therefore this is more stable than that. Okay? So the Zwitterion is the form that an amino acid would exist in solution. So this figure shows us what would happen to an amino acid at different pHs. At roughly neutral pH, you would have the Zwitterion dominate. If you lower the pH by adding acid, you're going to protonate the carboxylic acid. You'll generate the conjugate acid of our amino acid, and that's going to be this species here, which is positively charged. Conversely, if you add base, you increase the pH. That base will deprotonate your ammonium ion, and you'll end up with the conjugate base of your amino acid. Okay? So this is the neutral species, conjugate acid, conjugate base. Okay? And according to the Henderson-Hasselbalch equation, if we know those pKa values of the ammonium ion and the carboxylate, we can determine which species would dominate at which pH. There's also something we can calculate, which is called the isoelectric point. The isoelectric point is the pH at which the concentration of the Zwitterion is maximized. Okay? We're not going to calculate that now. We're going to delve into that in more detail when we study amino acids, peptides, and proteins later on in the semester. But as long as you know what the isoelectric point is, then that's what's important for now. To calculate it, all you would do is average the 2 pKa's. We've averaged the pKa of the carboxylic acid and the ammonium ion. In most cases, it ends up around 6. So we know that at pretty close to neutral pH, we're going to have the maximum concentration of this bitter ion. For now, it's just important to recognize which of these three species would dominate at either acidic, neutral, or basic pH. Any questions? All right, that's it for chapter 19. So good luck on the exam. It has a 3.5-hour time limit, but that's just to give you plenty of time to check your answers. I suspect most of you will take a little less than 2 hours to take it. So just to be cautious, make sure you allocate at least 2 hours to take the exam when you go in the testing center. It is open through the end of the day Friday, but don't procrastinate. Take it sooner rather than later. Good luck, and we'll see you on Friday.